Next section that we're going to deal with the Lewis dot structure is going to be a little tricky compared to what we've done up to this point. Pretty straightforward. But now we're going to introduce a kind of a wiggle to the definition of a single bond. But what we're going to do is what's known as oxyacids. Now, acids, which you've probably heard of, is something that we're going to hopefully talk about at the end of the school year. Hopefully it'll be the last chapter we get through another material. But technically an acid is anything, according to a scientist named Arrhenius, that gives off hydrogen ions. There are other definitions, but that's the one that we're going to go with in this. So obviously hydrogen is going to be involved in the compound, and when it dissolves in water, the hydrogen breaks off, and that's what creates the reactions that we see or feel if we spill acids onto a metal container or onto our skin. Alright? Now, the oxy tells us that there's going to be oxygen in these compounds. So what we're going to do is we're going to look at 3 different oxyacids. We're going to look at the Lewis dot structures, and we're going to examine how single bonds are created when it looks like it can't be created. Okay? So follow the logic on this. First of all, let's do one without that fancy little single bond. Let's do something called carbonic acid. Now this is the stuff in soda pop. The formula for it is H2CO3. And when it breaks down, when you put it in water, it does break down into water and carbon dioxide. So this is the fizz that we experience in soda pop. Right? And it's the CO2 bubbles that we feel, and the leftover from that is water. It also can do this. It can also, because it's dissolved in water, one of these hydrogens break off from this, and this leaves this polyatomic ion that we call the bicarbonate ion as a byproduct. So this happens as well. What we are going to be doing here is we're just simply going to be making the Lewis dot structure of this and not really paying particular attention. I'm just giving you a little background as to what carbonic acid does. Alright, so let's take a look at H2CO3. What is the central atom of H2CO3? Well, hydrogen can't be a central atom because it can only bond to one other atom. And the definition of a central atom is, remind you, we talked about this before, any atom that bonds to more than one other atom. Now, hydrogen can't do that. Hydrogen has one electron, will bond to one atom, and that is it. No more. So it can't be, by this definition, be a central atom. And when that happens, that we talked about before, you go to the next atom, which is the carbon. Carbon becomes a central atom. As carbon usually is for virtually every compound it is involved in, with the exceptions of anything that has cyanide in it. And a few other things, but not very much. So we're going to put carbon here. We go to the periodic chart and find out what A column it's found in. It's found in 4A, and therefore has 4 valence electrons. North, south, east, west. Okay. Now, oxyacids have a property that makes it a little bit different from all the other compounds we have done up to this point. These oxygens actually are going to bond to the carbon. The hydrogens here will have nothing to do with the carbon. It does not bond to the central atom. It instead bonds to the oxygen, which makes them a central atom as well as the carbon. But when we have an oxyacid, they will bond to the oxygen for reasons we'll get into if we take Chem 2. Okay? So we've got 3 oxygens, and I'll put them around like so. All right, then we'll go to the periodic chart, find out what A column they're found in. They're found in 6A. It says a positive 6, or a number of 6 valence electrons. Not positive 6, there's 6 valence electrons. North, south, east, west. We got single electrons over here, so let's put the 2 pairs over there. North, south, south, east, west, whatever. Then again 2 more, and again we got singles here, so I'll pair this and I'll pair this. We have to move things around. This is not cast in stone when you do this part. And then we have north, south, east, west. Oh, I got my directions right easy. And we'll put a pair here and a pair here. All right. Now, the next thing we're going to look at is the fact that we have 2 hydrogens. The 2 hydrogens, like I said, will not bond to the carbon. The oxygens bond to the carbon, and the hydrogens go to the very outside of the outside atoms. So 2 of the hydrogens is going to have, or 2 of the oxygens rather, is going to have a hydrogen bonding to it. So let's do this. Let's put a hydrogen here with its 1 valence electron, and a hydrogen here. I don't have to put them there, I can put them anywhere I want. Okay? Now, as I said previously, when you write single, double, triple bonds of anything, you start with the outside atoms bonding inward. Alright? And now we've got 2 layers of atoms, outside, inner outside, and then the central atom. So we're going to deal with the hydrogens first. We know they both lack 1 electron, so we're going to put a single bond there, and a single bond there. Okay? Now, that leaves 7 electrons for this oxygen, 2, 4, 6, 7. It lacks 1 electron, so it's going to form a single bond with this carbon right here. This oxygen, same thing, 7 electrons, 2, 4, 6, 7, lacking 1 electron to be full. This carbon now has 2, 4, 5, 6 electrons, and as we said, this oxygen here has 6. They both lack 2. That means that we're going to get double bond between those 2. Okay, so the circle form of the Lewis dot structure is completed. So now we're going to draw the line structure, making sure that we change the circles to identically sized lines, or as close as we can to it. And then the extra electrons that are not bonded to anything must also be represented. Do not neglect them. They get very long. So this is what we're going to have. Carbon, and then we got a single bonded oxygen over there, single bonded oxygen here, and a double bonded oxygen here, based upon what we draw here. Now you don't have to draw it in those particular ways. This is just what we did with this. Okay? Now, these 2 oxygens have hydrogens on. We put 1 here, and we put 1 up here. So all the hydrogens are represented. Now we need to put on the unshared pairs of electrons. As you see here, we got a pair here, a pair here. Over here, we got a pair and a pair there. And for the double bonded oxygen, we have 2 pairs of electrons. Again, it doesn't make a difference which direction you put it. You can put it where we left it here, or you can put it north and south, or north and west, whatever. I'll just do it the way that we constructed it there, so we got west and south. And there is our line Lewis dot structure for the oxyacid carbonic acid.